Channel B, Session Live 3B on the 19th of August 2020, or the ICCCBE and CIBW78 Virtual Joint Conference. I'm Dr. Riccardo Quadrignotto from the University of Bath, and we introduced the first article of our session, which is BIM-enabled design tools, information management and collaborative environments, simulation, parametric modeling, and other technologies for innovative AEC. Our first presenter is Dave Furstenberg, who presented the paper Information Management in AEC Projects, a study of applied research approaches. Passing to you, David.
Good morning, and thank you for this presentation. My name is David Furstenberg. I'm a PhD candidate at the Norwegian University of Science and Technology, and I'm also working as a BIM specialist in the multinational consulting company COVI. Next slide, please. We see that the construction industry has a low productivity and at the same time a low level of digitalization. So using the potential that lies within digitalization seems like a promising solution to reverse this trend. At the same time, we also see a transition from drawing-based design and construction to model-based design and construction, where all the information that was traditionally conveyed through drawings needs to be conveyed through models. And this information is twofold. It's graphical, like here on the right-hand side, or it's non-graphical, the metadata, which is actually very lots of information, and it only creates value when it's structured, and only then it can be machine readable. So information management of this information is necessary, and information management as a managerial task based on IT systems is important. And in order to have an overview of the theoretical foundation, I made this paper, and I used 3 research questions. What is the most common research approach? What are the most common research methods? And what's the most common form of data analysis? For that, I used I did a literature review in 4 steps, where I searched for information management in AEC on Scopus, and I verified the results on ORIA, which is a Norwegian library system. Then on step 2, I excluded all articles that were not peer-reviewed journal articles and that did not have information management in the abstract. As a step 3, I excluded all papers that were not in the design and construction phase. And the 4th step was a full text assessment followed by an analysis. I used a framework based on research approaches, and I used 3 philosophical worldviews: positivism, constructivism, and pragmatism. And as a form of data collection, I used empirical versus conceptual, and the research purpose was, which I analyzed, was descriptive, exploratory, or explanatory. For the research methods, I used the framework of quantitative, qualitative, mixed methods, and design as a method with the corresponding data analysis. So all this was the framework that I used for investigation. These are not the results. The results are coming now. The most common philosophical worldview had an equal share between constructivism, that was a typo I see, and pragmatism. And the research purpose was mainly exploratory and descriptive. More than half of the papers did not have a method chapter, and the vast majority of the papers investigated was conceptual. Then, research methods, it was mainly qualitative, and if design, which was the second most used research method, if design was used, mainly a software prototype was developed, and this software prototype was tested under simulated surroundings. All the papers had literature review, although only 50% of them stated this as a research method, and all the other forms of data collection, they were equally shared. The data analysis, like I mentioned before, the vast majority were conceptual with no data analysis, and the empirical papers had slightly more statistical than content analysis. So that leads me over to the conclusion. Most papers were conceptual papers developing software prototypes. So this means that there is a clear focus on the technology part of the digitalization and triangle. And there was a little attention on the philosophical worldview. Methods were not clearly described. That makes it hard for the readers to validate the results of the research. And the purpose of the papers was mainly exploratory descriptive, which indicates also that information management for AEC projects is a rather novel field of research without empirically based theory. And the last conclusion was mainly it was mainly conceptual papers with software prototypes developed under simulated surroundings only. So more empirical evidence through case studies is needed to provide a proper theoretical model, and a testing of these prototypes under real world conditions from real projects is also needed. So here I'm on the end of my presentation. I thank you for your attention, and here are my contact details if you have questions that cannot be answered in the Q&A afterwards. Thank you.
Thank you very much, David. Just remember to remind everyone that if you want to pose questions in this forum, hashtag 3B1, they will be directed to David towards the end. Thank you very much, David, for your presentation. We're moving to the next one now, by Beidi Lee. I'm presenting qualitative and traceable calculations for building codes. Can I ask you, Beidi Lee,
yes.
to join us, please?
Am I joining? Great.
Thank you very much. And I'll see you later,
Great.
David. So thank you very much, Beidi Lee. So we're going to just upload your presentation now.
Thank you,
and
thank
the
you,
floor is
Ricardo,
yours.
for this introduction. I don't see my slides. Okay, great. So my name is Beidi Lee, and I am a PhD student at Aarhus University in Denmark. And I'll be presenting a paper together with Johannes Mignardi, Robert A. Moore, and Carl Schutz, entitled Qualitative and Traceable Calculations for Building Codes. Could we go to the next slide, please? Great, thanks. So the motivation is that in automatic code checking processes, if code engineers use ad hoc assumptions and magic numbers to translate instances from regulation terms to building properties, this might lead to obscure and unverifiable checking results. So that this is why we're proposing a new approach to have a class mapping from the regulation domain to the building domain, and to build a data structure directly into our chosen logic framework called ASP-MTQS for runtime optimizations. So this will allow code engineers to focus exclusively on code semantics without worrying about runtime or how the rule is being executed. And this also provides a way that is extensible and scalable to maintain a large code base against real-world buildings. Next slide, please. Okay, thank you. So here is a building code from New Zealand that says there shall be no direct line of sight between an accessible route and a bathroom object. Reflected in this picture, this means that no bathroom fixtures can be installed below the vision limit line. So this code being performance-based, it is actually hard to check because it evokes concepts about human experiences and behaviors such as line of sight that is ambiguous, accessible route that has to be inferred from the building model using additional assumptions, and it's not always optimal to check every combination of accessible routes with bathroom objects. So one possible interpretation of this code is to say that people using bathroom objects should also be visually occluded. And we capture this using functional space to model minimum clearances around objects represented here as 3D boxes having dimensions that are based on the architectural guidebook Neufit from Germany. So in order to prepare building models for code checking, we will augment being first with what we call spatial artifacts that can be understood as a subtype of IFC space, such as movement space, a region that is accessible by user, or visibility space, a region that is visible from objects, based on findings in psychology and human economics. So this code is actually translated into a topological constraint that says the movement space should not overlap with the visibility space. So the green region and the red region should not overlap. And we can encode this as a logical proposition that says if there exists a bathroom object B, a movement space N, a visibility space V, such that V overlaps with N, then there's a code violation. So we want to encode this in a logic programming language called ANSYS set programming, ASP. So a role in ASP is read as an implication that says if the body of the role is true, the head of the role must be true too. So we just, in a pure declarative and transparent way, we can encode this role as an ASP role that can be executed in our extended version of ASP that understands space. So in our proposed workflow, code engineers will translate natural language code using alternative definitions. This will provide a transparent and modifiable role interpretation. And building engineers will augment BIM models with spatial artifacts that are evidence-based, coherent, and uniform. And finally, ASP is in charge of checking the formalized constraints against augmented building and producing a compliance assessment. So now I'm going to explain how did we improve scalability of rule execution by building a data structure into ASP. Now imagine we have some target relation R that is difficult to check or that is difficult to compute, but some sufficient and necessary conditions to R that are less costly to evaluate. So we can use them to shortcut some superfluous evaluations, namely true negatives and true positives. Right. So here are two examples of trivial cases where two regions or one or two are disconnected. One is when their bounding boxes are disconnected. The other one is when they do not span over the same quad cell. So those conditions actually reflect general data structures such as R trees and quad trees. In our empirical test with circles, we have generated a random number of circles and distributed them into different clusters. And by adding necessary and sufficient conditions to two circles overlap, we have achieved a 4-factor speedup for 2,000 circles and 10 clusters. And finally, for our scalability test with a real building model that has merely 7,000 building objects, we have derived 490 visibility spaces, 100 movement spaces, and we have observed that the runtime has dropped from 9 seconds to 1.5 seconds when we incorporate spatial data structures. Okay, so to conclude, in this paper, we have proposed an automatic building code checking workflow that separates code semantics from runtime optimizations so that we have a uniform, coherent, and traceable code formalization that is independent from a transparent, logically verifiable, and scalable rule execution. Now, in the future, we are intending to enrich spatial artifacts by different types of users, modalities, and situations. We're expanding our vocabulary to have a higher coverage of the building code. And we're also looking into reasoning about low-level detail designs with missing information. And finally, we are trying to generalize our method to other kind of implicit design constraints, such as architectural rationales. So thank you very much for your attention, and I'm looking forward to our discussion and your questions. If you're unable to attend my presentation online, you are welcome to send me an email, and I will be happy to share any implementation details. Thank you so much.
Thank you very much, Beidi. Excellent presentation. We're going to now move on to the next one. Just to remind everyone, if you have questions for Beidi, hashtag 3B.2. So our next presenter is Rihel Zelecki, and the presentation title is Semantic Web and Linked Data for Information Exchange between the Building and Manufacturing Industry, Literature Review. Rihel, the floor is yours. We can't see you at the moment, but hopefully we'll be able to hear you.
Yes, thank you. Hello, everyone. This is a paper presentation titled with the Semantic Web Technologies for Information Exchange between the Building and Manufacturing Industries. The paper is co-authored by Annika Muscati, Peter Johansson, and myself, Rahel. I am a PhD student in Jönköping University here in Sweden. Next. This is the first work of an ongoing PhD research project that aims to enhance the information exchange between the building and manufacturing industries using the semantic web technologies. And to better understand the benefits and limitations of these technologies, a literature review was conducted with a research question: what are the benefits and limitations of using the semantic web technologies for information exchange between the building and manufacturing industries in comparison with the conventional approach of information exchange using the OpenBeam standards? We formulated the research question using the PCOG framework, which stands for Population Intervention, Comparative Intervention, Outcomes, and Context, which also guided the important components to be included in the review, such as comparing the semantic web technologies with the existing technologies. To identify relevant papers, a systematic search was conducted, and using the Prisma flow diagram, papers that are relevant to the study were selected, and 26 papers were included for the review, and the results are presented from here on. The results of the review are organized in 3 sections: benefits of the semantic web technologies, that included 3 use cases that are relevant to this research project, limitations of the semantic web technologies, and limitations of the existing technology. And under the benefits, there are 3 use cases that we identified. The first one is ontology-based information management and sharing, which offers an opportunity to model and combine heterogeneous information using a shared vocabulary that enables to provide a homogeneous view of information, making the information accessible and usable to the end users. Ontologies have the potential to enrich both the semantics of product geometry and product data that enables to represent the real-world product in a homogeneous and machine processable format. It also facilitates an automated searching and using of product data at the early design stage. It enables data integration, execution of sophisticated data query in multiple domains, consistency checking, logical inference that allows manufacturers to develop an idea or concept for their new products. The second benefit is to combine product manufacturers' data with building data, which enables to link data that come from both the building and manufacturing domains in homogeneous view. And it also supports the manufacturer supply chain by linking product data with other data sets, creating customized data sets for specific stakeholders, and providing suppliers with detailed structured product data. And the second benefit is support building performance analysis and organization. In that, optimization and product descriptions required to conduct performance analysis can be accessible, usable, and searchable on the web, which gives designers an opportunity to explore possible design alternatives. And it also increases the engagement of the manufacturers. The limitations is the first one is the lack of standard BIM-related shared knowledge base, which results in misinterpretation of concepts and loss of information during information exchange between different applications. Limitations of the, so to address this issue, the IFC schema was converted to IFC All, which ended up becoming large and complex that affected the searchability and extensibility of information. And to address that issue, researchers suggested to develop ontology for specific instance instead of changing the IFC. And ontologies are also usually created manually, which indicated the need for automatically developing them from databases. On the other hand, full automatic ontology generation has been a research problem, and the creation and maintenance of links also reported as a problem. Another challenge is it puts demands on the manufacturers to create product data ontologies, which manufacturers are not interested because they already created their own information systems. And coming to the limitations of the existing BIM technologies, IFC is the existing standard, which actually enabled successful exchange of information associated with product geometry. But when it comes to explicit semantics of product data, it is reported that it is not easily to represent that kind of information using the IFC. Extending IFC also reported as very challenging, especially when it comes to on the real time. And consistency checking, reasoning, and semantic queries also reported as difficult to apply on IFC building models. Our conclusion is most of the papers that we reviewed showed that the semantic web ontology-based approach diminishes the major challenges of the current standards. And at the same time, they also suggest that the application of semantic web to be used as a supplemental to the existing technology. For our future research, first, what we're planning to do is to develop domain-specific ontology for building lighting products, and then to transform the product data that we gather from our case campaigns into the semantic web format, and then to use the semantic web technologies in combination with the parametric design to integrate product data with BIM tools. Thank you for your attention.
Thank you very much, Rahel. I must apologize. The title came as Rahel, so it's Rahel. Thank you for a very interesting presentation. Just to remind everyone, if you have questions for Rahel, #3b.3. And we will have a question session towards the end of this panel. So our next presentation now, I would like to invite Joseph Jabin, who will be presenting classifying IFC entities by their relative importance for accurate interoperability measurement. The floor is yours, Joseph.
Yeah, hi everyone. And yeah. Hi, I'm Joseph Jebin, and this is my paper on classifying IFC entities by their relative importance for accurate interoperability measurement, co-authored by Johannes and Robert Hemmer. Next, please. Today, I'll be talking about why we need to classify IFC entities by their relative importance. And I'll be starting with the background, the problems to be solved. Then I'll be introducing the relative importance framework as a solution, then move on to the application, implementation, outcome, and future work. How interoperable is my tool? That's a major problem we talk about in the BIM industry. And many people like to know how interoperable their tools are. However, the users are only concerned about the interoperability of their elements related to their discipline. And currently, the major data exchange standard adopted by many software tools is IFC. And many tools are certified for IFC interoperability. And these certifications are done based on conformance test. However, conformance test does not convey limitations of the certified tools, and the users think it's 100% accurate. And even if the levels could be reported, not all errors carry the same impact for the same stakeholders. For example, an error in a beam is more important for a structural engineer and it is not important for a plumber. And currently, there is no method to classify IC elements by its relative importance. And for software developers, it's not possible for them to solve all the problems at once. The solution is to have a framework that could rank the IFC elements as per their relative importance by discipline. With this, the stakeholders could divide and conquer. They can use this divide and conquer approach to focus on the interoperability problems of only the elements that are important for their discipline. And it can be used to augment the current certification logo and make it more meaningful. And so what if instead of just showing a certified logo, show the accuracy in numbers along with the logo? And this is an example for applying the RI framework to augment the certification logo. The table shows which discipline the tool is certified for, and it shows the accuracy of IFC elements that are important to the discipline under 3 columns, which are high, medium, and low. And it shows an overall score, which is an average, weighted average of all 3 important levels. With this approach, the end user could take an informed decision whether to go ahead with the current data exchange, even if there are some errors with elements that are unimportant for their discipline. This is how the relative importance ranks are assigned to the IFC elements. So for example, IFC beam placement is very important for a structural discipline, but it's not as important for an interior discipline or a plumbing discipline. Why? Because the interior works contractor do not actually construct the beams, but they may have to check the position of the beams so that whether it's to interfering with the interior objects. Similarly, the plumber might have to do some structural penetration on the beam. So if they penetrate the wrong point, it might cause a problem with the reinforcement bars. After ranking the elements, the accuracy of the IFC elements are tested using a round trip test. This method is where an IFC file is imported and then exported immediately without any change. And technically, if the data exchange is accurate, both the files should be saved. And which is not always the case. Many researchers have done round-trip tests and have reported that there are many unintended alterations to the IFC element due to the errors in the translator modules. This is an exemplar for the round-trip test results, which is shown in the table. The numbers show that some of the elements have not been accurately translated. And by linking the same back to the ranking table, a score could be calculated that shows how accurately the important elements were translated with a specific tool for a particular discipline. And finally, this is how the actual calculated score looks like. These 3 tables show the certification outcome of the same tool. I repeat, the same tool from the perspective of 3 different disciplines. If you look at the high conformance, high importance columns, it clearly shows that the tool is more accurate for exchanging IFC elements related to the structural discipline than elements related to a plumbing discipline. Thus, a structural engineer could proceed with data exchange with this tool, even if the other columns show less accuracy. Likewise, a plumbing contractor will understand that even though the medium important elements are showing high accuracy, the elements that are related to plumbing is not exchanged accurately. That means just 80%. And this plumbing contractor can decide whether to go ahead with the data exchange or wait for an update from the software vendor or look for another tool altogether because this is not doing it well. So concluding, how interoperable is my tool? The outcome of this framework gives a solution. The user could refer to the table shown along with the certification logo and get a clear picture on how accurate the tool translates the element that are important for their discipline. And for software developers, they can solve most of the important error first and then go on. And the future work for is to develop a functional prototype which uses this framework for that certification. And this is my presentation, and thanks for listening.
Thank you very much indeed, Joseph. We will have questions towards the end. So if you have questions to the audience, it's hashtag 3b.4. I would like to invite now Thomas. Oh, Thomas, that is a very difficult surname for me to pronounce. I would say
That's pretty good.
Kreinen. And good.
Yeah.
And is validation and interface of geometrical relationship in AFC.
Thanks.
So, floor is yours.
Yeah, thank you. So Thomas Kreinen, which was pretty accurate, the introduction. I'm from Delft University in the Netherlands, and I'm here to present validation and inference of relationships in IFC. So validation to build trust in our information exchange, similar to the previous topic perhaps, but also to deduce relationships on the fly. Next, please. And this we call inference, or maybe even, let's say, a bag of elements instead of a dense graph. And this will create models that are more easily updated, combined, and partitioned due to the less dense graphs. Because in reality, your building model is actually spread out over various aspect models or discipline models, or is spatially partitioned. Yeah. So considering space boundaries as an example, suppose on the right you have your tool that's in charge of the programmatic spaces, and on the left you have your bounding elements. So how can an authoring tool then export these space boundaries if it doesn't have a complete view of the required information? And that's why we want to deduce more relationships. So our work is implemented on top of an open source IFC implementation and geometry library called IFC OpenShell. And in the top of this slide, you can see a direct link to some parts of the implementation. And traditionally, IFC OpenShell is always implemented based on a BREP model for the geometry, boundary representation. And here you can see an example for a cylinder. So you only need two vertices. You have curved edges and surfaces, and vertices have tolerance. On the other hand, we started to look now into Seagal Neff polyhedra that actually define your volume as a tree of half spaces, 2-dimensional and 3-dimensional. So BREPs match the semantics of the IFC geometry really well, but we really found, due to no tolerances and arbitrarily precise number types, we found the Seagal polyhedra much more robust with extensive processing. So now back to IFC. There's really a lot of relationships in IFC. And we believe that many of the ones that are related to proximity, connectivity, containment, so all that have a, let's say, geometric meaning, can be computationally derived. And in this research, we focus on 3 of them. Now, our method is based on Egenhofer spatial predicates, where the spatial relationship between 2 operands is qualified as the result of intersections between boundary, interior, and exterior. And this boundary we consider as the Minkowski sum of, let's say, the operant volume, the operant surface, and a small volume. And this creates, let's say, a narrow, hollow solid along the exterior of your volume that you can use to intersect with other elements. So here, for example, you see that illustrated in the case of our wall connectivity connection. Now, we ran our tests on 3 publicly available in well-known building models. So the duplex model, one version of the FZK house, and a Smiley model. These are all architectural submodels, not overly complex, so keep that in mind. And then you can see here the first check or inference was the spatial containment. And you can see that in the duplex model, a couple of elements are misplaced. And this is actually well known. This is also observed in other literature. For example, a paper from Solihin, Eastman and Lee from 2015. Then the results for wall connectivity in this table. A relationship can be missing for two walls that are actually touching. It could also be an invalid relationship, so with the wrong connection type, start or begin, or a wrong relationship. And you see that here illustrated again in case of the duplex model. So on the left, the wrong connection type at start or at path wrongly specified. No connectivity information for two walls that are touching. And two walls that don't touch, but are actually said to be connected. And then the third inference or validation we implemented was space boundaries. You can see here again from the duplex model. So the duplex model is from 2011, and the situation has likely improved, but this was pretty, unusable. And for the Smiley model, more recent model, situation has improved, but still, in this case, only some missing space boundaries. But again, that completely invalidates your thermal connections, of course. Now, a note about performance. Overall, performance wasn't prohibitive, but a fair amount of time was spent on the Minkowski sums and arbitrarily precise number types of Seagal. So conclusion, we have inferred connections, explicit connections in IFC to enable more distributed and transactional working, so incremental updates, extracting or merging models. And the geometric validation shows that most models contain flaws. And this is, for practitioners, probably not a surprise. Thanks so much.
Thank you very much, Thomas. Very good presentation. So I would like to invite now Colleen Boj, and the title of the presentation is a 4D BIM system architecture for the semantic web.
Hello, hi everyone. Can you hear me? Yeah, good. Okay. Where can I see the slides? I'm sorry, I haven't used this system before. There we go. Thank you. It's good to present to CIB finally, even if online. So this is part of a project that we're currently working on at LIST in Luxembourg, part of the 4D Collab project. So this is the third publication looking at the architecture of the prototype that we have been developing, along with Sylvain Kubicki and Annie Guerriero. Could you please go to the next slide? So model data workflow. So I thought I'd go over a little bit on the context of what the system is supposed to do and why we've come to decisions we've made. So I'm going to present a little bit about the workflow of information and what we call 4D BIM synchronous collaborative sessions, meaning people that work together on a 4D model, and they essentially use touch surfaces to do that. So we've tried to map a little bit the workflow. So things are quite complex. They come from several BIM platforms, 3D to 4D and so on, but we've tried to use things that users find usable and easy to use as touch interfaces. So we don't want to bring all the details in. So this was one of the problems we had initially. So we were using IFC and all sorts of geometric model translations to showcase them on interfaces, and using some temporal information and so on. But the problem then was, well, they collaborate on these sessions and all these sophisticated devices. How can we return? What are the outputs of each of these collaborative sessions? How are they returned? And well, how are they captured? So on. So we've tried to use, for instance, BCF to return specific information back to the tools that they use. They go back to their offices and then they try to keep track of what they've decided in the models. But of course, these questions, they're hard to answer, so BCF might not provide everything. Sorry, could you go back for 1 second? And so the definition of the meeting itself is done using an ontology. And of course, we have limitations with regards to the device capability on the user interfaces, so on the front end. So then just going over the 4D Collab ontology model, the features of interest, how they're used, and well, we've aligned it with IFC a little bit. So next slide, please. This is not part of the conference article, but there's 2 references there that you can check out from previous publications where we describe the model, the sort of the why we're doing it this way, what are the concepts of interest, and so on. And this is an initial version we've presented last year at another conference, but this has changed significantly because of we've been developing around it and we've been trying to use it. So it's an iterative process. So the next slide will show you an unpublished current version of the ontology with the main concepts. And we try here to model what we call a social technical system, meaning that we're not only modeling the 4D BIM itself, but we're modeling the people around it, the people that collaborate, their interactions. So we try to keep track of everything and semanticize the things that are capturable, recordable, and let's say measurable around these collaborative sessions. So for that, we needed some sort of architecture. Finally, getting to the main point of the article, where we define several conceptual layers, the roles, and what impact they may have on a system design. So I will not go through all the details of these. You can find them in the article if you're interested. I will give you sort of an overall impressions and of how things work. So really what we have is a typical, let's say, system architecture, which works around the semantic web layer, which is component number 4. The first component is the system application, the server application layer, which we call a backend, which we've developed in .NET with several open source libraries, such as the XBIM library or the .NET RDF to support our semantic web layer. So essentially, in terms of implementation, and we have a BIM data layer, which is at number 3, looking at IFC and BCF. So essentially, these constitutes of 1, 3, and 4 constitute one application for us in implementation in practical terms. And then at layer number 2, which is client application layer, we essentially try to interface with several front ends that we use across project partners. So this, of course, has shown us the limitations of our ontologies, of our tools, how fast does it work, because we still are in an environment where people need to use the models to manipulate them as fast as possible. We've been trying to use existing tools on the market, such as the Forge viewer from Autodesk and other ways of visualizing and manipulating the model on different touch devices. Now, a little bit about this. Semantics, yes, just 1 second back, please. So the semantic web layer is where we keep all the information in a contextual way, and we have another paper which you may be interested in, why semantics are vital for digital twins and for monitoring construction sites, or even in this case, we are essentially monitoring what people try to do during collaborative sessions. So the semantic web layer essentially stores the data in the 4D Collab ontology, where we've mapped it to, say, IFC, OWL, and we can add or extend as needed, depending on the context. Now, of course, the semantics here is very high, but we cannot present that on front-end interfaces because most people use JSON. If you're looking at web devices or web applications, you'll use JSON. And there is JSON LD, which is possible to be used, but because this one sends more data, because it sends more semantics, it just could make it a little bit slower, but at the same time, the application on the front end can't really use it unless you program a little bit around it. But then we also have a Sparkle endpoint, which we expose to our users to then explore the ontology itself. So that's sort of the idea, so a compromise between effectiveness, open architecture, and of course, trying to be usable during these sessions, as people touch models all the time. So this is just a sneak peek onto what the front end we've developed looks like for demonstrations. We'll be testing it soon on with live people, but we've been a bit delayed with the COVID crisis. and we have one of our partners that have a touch table which supports applications. So this is a web-based application, but we've got a few others that work around it. Yeah, I think that's it. I hope I've touched on all the critical points there. If you want to see the technical aspects, please see our conference paper and have a look at our other references. And if you've got any questions, please email any of us in or out of conference hours. Thank you.
Okay, Colleen, thank you very much indeed for your nice presentation. So I would like now to start the plenary session and invite everyone to come back, please. So I'm going to screening that we have various questions. It's been a very busy chat session. I can see that some of the questions have already been answered by the authors directly to the chat. The first question is, Jacob is asking Beidili, how do you choose the cell size of the spatial partitioning in oak trees?
Yeah.
Yes.
Yeah, I think I already answered in the chat, but so for the empirical test, we partition the space into clusters, so into like equal-sized clusters. But like the real idea, like the core idea is that those clusters will give necessary and sufficient conditions to decide that two circles are indeed overlapping. So for example, if two circles are contained in clusters that are not adjacent, then they're necessarily disconnected. So this means that you only need to check circles that are within the same cluster or with like neighboring clusters. But for the real building, we actually have employed, like we actually handcrafted a series of necessary and sufficient conditions to decide that 2D regions overlap. So we didn't use a space partitioning for the real building, but we could have done that too. And that would be very much specific to the building that we're using for our evaluation.
Thank you very much. So our next question, there are two questions combined also from Jacob to Rahel. Really valuable and well-structured overview. You choose the scope of records. And for your initial paper seed, what is your impression regarding the coverage this provided regarding the topic? Do you plan to broaden the research scope? That is for Rahel. I think maybe Rahel has left the session, maybe. So I'll move on to the next, and I will make Rahel aware that there's been a question for her. So I have actually a question for David. Dave, you pinpoint something very important, that is the lack of philosophical positioning in most of the articles in our field. What do you think is the consequence of that?
The consequences, I forgot to mention one aspect in my presentation, and it was that of all the papers, the final sample was 27 papers, and only 2 papers stated their philosophical worldview. So the other ones I had to interpret based on existing literature. But the consequence, I think, is that researchers may be they may use a philosophical worldview that is not really suitable for their research. Like in my case, for example, it's an industrial PhD that I'm doing. So I have clear restrictions of my approach to research, and I think other researchers, they have to be aware of the philosophical framework that lies beneath their research, and the awareness must be strengthened about this.
I agree. I think in general we lack in terms of innovative thinking, as you say. So thank you very much. Now is for Joseph. We have a question here posed by David and another one by AKP, and is which framework did you use for classification of disciplines? And the other one is, are you planning to attach some error reports showing exactly which elements are wrong?
Okay. So for the classification of disciplines, I have used the omni-class classification and the table number 33, which classifies the disciplines in construction industry. And yeah, that's about the classification. And then the question about planning to attach some error reports showing exactly which elements are wrong. Yes, so the table which I've shown is the summary table, which will be very like the overall view and can be shown along with the certification logo. And for the online version of this, you can click on it and it will go into a drill down report, which shows which elements were translated incorrectly. So you will get a full detailed report on that.
Thank you very much. Our next question is for Thomas, and is Robert Amor is asking, does this approach work with all geometry supported by FC? So representations like point clouds seem more difficult.
Yeah, you can also look back at the chat. There is some answers there as well. But in principle, yes. So a nice thing about this Minkowski sum is that it's fully generalizable to lower dimensional geometrical entities. So you can take the convolution of a point and a volume, or two lines becomes a face. So that's fully possible. In case of point clouds, when you're talking about, let's say, well, thousands is optimistic, millions of points, yeah, then performance will be abysmal. It won't be performant. We did use similar to Bailey Lee. We have some spatial acceleration structures, so that you can indeed filter out geometries that are clearly disjoint when you do intersection checks or connectivity checks. But yeah, this won't scale to hundred thousands of points. That's still not feasible.
Okay, thank you very much. I'm going in. There are more questions, so I'm coming and going back in order. So I have a question for Kalin. You mentioned in your presentation that you are incorporating more information about people, right? So where is the data coming from, and how are you incorporating that?
Yeah, so what we do is that a user is able to create his own session and bring his own models to the table, let's say. And that would be considered such as a BIM manager sort of person. And then people around the table also are seen as participants in the model. And essentially, these participants are allowed to raise issues, such as you would raise an issue in BCF. And they are all allowed to manipulate the model because they are essentially doing a co-located synchronous collaboration session. And I think in the ontology, they are defined as participants in this case. And there are relationships represented between them and the things that they have a right to modify.
Okay, thank you very much.
I hope
the next
that answers the question.
No, it did, but I will be in touch for more details. I have a question for Joseph now, which is a follow-up question by David. Did you consider use cases in addition to disciplines?
Yeah, hi. So I'm right now, my research is into implementing this and making a working prototype. So I'll be using creating some use cases and then testing the measurement for those particular use cases? Yes, so I'll be using use cases.
Okay.
Thank you.
For Jacob is saying that it's very cool, Thomas. So so that everybody knows the answer. Will there be an IFC open shell with a CGAL kernel?
Yes, yeah, and we have, especially in these kind of use cases, so a lot of processing. Yeah, we expect some clear benefits. We've been using this on a prototype to convert IFC to CTGML. So then you need to get from the individual building elements to one valid topological separation between interior and exterior, and we use similar methods there. And then it's really required to use these kind of robust kernels because the fundamental notion of in OpenCascade that to have this precision that will increase when you apply cascading geometric processing will mean that at some point you get into an inconsistent state when two vertices are the distance between two vertices is similar, same order of magnitude as your precision. You cannot really separate interior and exterior anymore. So that's really where these kind of alternative implementations are required. On the other hand, I do expect some issues with the more advanced geometric representations. There was a follow-up question from Jacob. So not so much half spaces that can be handled, but there are some pretty advanced sweeps, for example, where you sweep a face along a curve while you have to keep the normal vector of the curve into account, but this is hard on a geometric kernel that doesn't have support for these kind of that only supports polylines. So in the end, what will probably happen is that we'll have some sort of hybrid kernel that will have CGAL that can fall back to OpenCascade, and the other way around to kind of get a best of both worlds implementation.
Okay. The sound went off a bit here. Well, Rahel is back. So Rahel, the question for you is by Jacob. Very valuable and well-structured overview. You chose the Scopus records. So what's your impression regarding the coverage this provided regarding the topic, and do you plan to broaden the research scope?
Yes, thank you for your question. I have an impression that the coverage is sufficient to answer our review question. This is the first work in our ongoing PhD project. So for us now, we're convinced that the semantic web technologies are good enough to represent the semantics of product data in machine processable way. But sure, we will broaden the search as we proceed on to the implementation phase. Yes, I have a plan to broaden the search.
Good. We have another two questions for you, Rahel, from Sylvain, which is from the screening of 26 remaining papers. What is the conclusion regarding the inclusion of a building products data templates in semantic web-based information exchange systems? And are there research implementation demonstrating it?
Yeah, I came across papers that showed developing product catalogs using the semantic web technologies, and my ambition is to develop data templates using the semantic web technologies, and I'm considering to use the new standards published recently, such as the ISO 23386 and ISO 23387. So I'm planning to take advantage of those standards to be able to develop product templates while using the semantic web technologies. And yes, I came across papers that showed the implementation of demonstrating developing product catalogs using the semantic web technologies.
Okay, thank you very much. I'm not sure if Thomas, you've covered this question already, but Jacob is asking. I think it is used intensely employed in your group in GIS context for model checking. How feasible do you think NEF polyhedra are for IFC weirder geom-rep such as half-space solids?
Yeah, I will comment mostly on the first bit. So indeed, CGAL and these kind of polyhedron implementations are really the basis for a lot of the GIS systems that exist in the world. So in particular, these kind of post-GIS implementations that implement spatial querying in SQL or GeoSparkle are all implemented in CGAL when it concerns 3D geometries, at least. So I indeed see this as a core advantage, that we can kind of get seamless interoperability between IFC and our predominant spatial querying implementations. But yeah, that's for future research. I did some prototypes earlier in my PhD with GeoSparkle on IFC building models, and I think that's interesting avenue for further research.
Okay, well, thank you very much. We have a final question now, is for Kalin. Philip is asking you, have you maybe considered usage of information container for document delivery, ICDD, for storing and exchanging 4D models according to underlying ontology in your approach?
Yes, thanks. That's a very good question. We haven't looked at this standard specifically, but we have considered other ontologies that model documents and how they are referenced, such as documents referenced as a geometry or as a reference on the web. We do have a document class in our ontology, which we can align with, I suppose. However, the difficulty here comes in the fact that people usually don't bring a 4D to the table, because the documents are separate. There is no 1D for document unless you're using, say, Autodesk Navisworks. So it becomes quite difficult on whether people bring fully linked documents or not. So our interfaces allow you to create it on the spot, but then the challenge then still stays with, after the session, do they split the model again? So how will they take it back to their, let's say, office? Because one is in charge maybe of certain aspects of the 3D, and then they have a planning document which then they can all see. So we don't know exactly how to model that. We've tried to take a very pragmatic approach on, well, they are using documents, such as they often bring PDFs and floor plans, because they still use those in practice. So it really is an amalgam of things to consider. But that could be a good way to look at. So thank you for that suggestion.
Okay, I would like to thank you everyone from this first half of the session. Right, so I think it's good to see that we are enhancing the way. Not just the technical aspects of modeling needs improving, consider improving, and I find also that we are kind of shifting towards the use of a more standardized approach, and which is leading to technological developments, but also process developments that enable people to make full use of building information modeling. So we're going to have a 2 minutes comfort break now, right? Just to allow everybody to get a glass of water or to pop out of the room. And then we will come back in exactly 2 minutes. I'll see you shortly. Okay, so we are now starting the second half of the session, the live session 3B. And I would like to invite now Thais Sartori. She will be presenting the article Analysis of Whole Building Lifecycle Environmental Impact Assessment Tools. So, hello, Thais.
Hello, how are you?
I'm fine, thank you very much. Hope you're well. So we can have your presentation on the screen now, and the floor is yours. So then we will upload it for you.
I'm sharing the presentation or you? Oh, okay,
No,
good.
we are, yes.
Okay. Okay, hello everyone. My name is Thais. I'm a PhD student here at Queensland University of Technology. And the title of my paper is Analysis of Whole Building Lifecycle Environmental Impact Assessment Tools. The presentation is not on.
Technical problem, apologize for that. So they will bring it back.
Okay. Okay, can you jump to the next one, please? All right, so first of all, I'm going to give a brief introduction of what EIA tools are. They allow decision makers, such as designers, architects, or engineers, to understand the environmental impacts of their choices. And the way they do it is by connecting the environmental context to the decision-making framework. And there are many types of EIA tools represented as interactive software and passive tools. But the EIA tools that assess the whole building life cycle is life cycle assessment and green building rating systems. And these are the tools I'll focus on this study. So the goal of this article is to discuss the two types of whole building life cycle EIA tools mentioned previously, comparing their methodological concepts as well as the effort of combining both approaches. And first, I will explain the tool separately and make a comparison analysis. So life cycle assessment addresses the potential environmental impacts of all inputs and outputs flows within a product's life cycle. So as you can see in the image, whole life cycle goes from raw materials acquisition, manufacture, use, maintenance until end of life. So these are the 4 stages of LCA. We have goal and scope, inventory, impact assessment, and interpretation. And the methodology can be applied to materials and processes, or is an aggregation of materials and processes such as buildings. And now talking about rating systems, they are voluntarily labeling schemes that measure the performance of green buildings by assigning credits and weights to environmental indicators sorted into different categories. So in this study, we analyzed 6 different rating systems, and they are these ones: the LEED, BREEAM, HQE, Green Star, DGNB, and CASB. And these rating systems, besides being well-known worldwide, are on the top list of the most cited in the Scopus database as well. So looking at the rating systems mentioned in previous slides, energy, water, and materials are the most common categories analyzed by rating systems, followed by site and indoor and outdoor environment quality. And again, looking at the rating systems mentioned, energy accounts for 25 to 30% of the total credits available. And based on the main pillars of sustainability, rating systems mainly look at the environmental impacts with reduced emphasis on analyze economic and social issues. So now comparing both whole building environment impact assessment tools, we can see that rating systems are more flexible, so you can choose which category your building is more likely to obtain credits. But LCA calculates a building's environmental impacts in a more systematic and holistic way. Also, in rating systems, the outputs emphasize the environmental improvements of the design decisions because it awards the building with a certification level. But LCA outputs are focused on environmental damages such as ozone depletion or human toxicity. And another difference is that rating systems can evaluate specific local ecology and infrastructure impacts, such as the influence of the buildings on the microclimate, as well as the ability to modify the surrounding transportation system. And LCA has a limited set of impact categories because it focuses on global or regional spectrum. So some rating systems have been applying LCA as one of their criteria. By introducing LCA, rating systems increase the credits given to simulation of buildings performance, founding the assessment on empirical calculation methods. And apart from the well-known checklist practices, LCA compels decision makers to search for more authentic, sustainable solutions, stimulating the search for innovation in the design. And this study also analyzed LCA requirements for the 6 rating systems previously cited. And the certification version chosen was new construction, non-residential buildings, and these were the categories analyzed. And I'm just going to emphasize the method category because we found 3 main methodologies used by rating systems to address embodied impacts, and they are reporting, comparison, and rating. BRIAN is the only one that evaluates the impact with the aim of reporting it. And the comparison methodology confronts the impacts of design baseline with an environmentally improved design. And DGNB uses the rating methodology when LCA results are compared with reference values. So after analyzing all the LCA in rating systems and the requirements of LCA within rating systems, it was concluded that rating systems assign credits into 2 different ways: qualitatively in a checklist format or quantitatively, such as LCA. And when adding LCA as one of the rating systems criteria, the performance is supported by scientific techniques, which increases the scientific value behind the credits, providing numerical evidences. But the drawback is the complexity of assessing these credits. So from the rating systems analyzed, only 2 mandatorily considers LCA, including the impacts of energy use during operation. But the most efficient way to evaluate the impacts of a design choice is through a systematic LCA approach, considering all life cycle stages. So it was found that the combination of LCA with rating systems would bring substantial benefits in identifying and reducing buildings' environmental impacts, but the existing tools still struggle to deliver an assessment that combines both approaches, especially during buildings design process. Thanks for listening.
Thank you very much, Thais. So just to let everybody know, so if you have questions for Thais, you can type on our chat and use hashtag 3b.7 before your question. So at the end, we can pass the question to Thais. Thank you very much. I would like now to invite Julia Reisinger, and she will be presenting framework proposal for a BIM-based digital platform for flexible design and optimization of industrial buildings for Industry 4.0. Is Julia there? Can we bring her in? Please?
Hello, good morning.
Hello, Julia. Yeah, we will just upload your presentation now. And the floor is yours.
Thank you. So good morning to my presentation. I'm a PhD student from the Vienna University of Technology, from the Institute of Interdisciplinary Building Process Management, and we are researching a digital platform for the design and optimization of industrial buildings coupled for Industry 4.0. The problem is the production of the future has very short product life cycles, product individualization, very fast changing production processes. And all these new technologies need flexible and adaptable manufacturing systems on production system side and building system side. But the building, the process, and the products diverge in different life cycles of a factory. So the life cycle of a building is much longer than production processes. So they're changing a lot during the life cycle of a building. So we need flexible building structures. And as the building industry is one of the biggest contributors to environmental influences and industrial buildings play a major role, we focus on that production systems which change very quickly can be adopted by the building structure. So we aim to plan very flexible structures, but therefore we need integrated industrial building design. So right now we have a sequential design process with multiple iterations, and we aim to have an integrated design process with one holistic factory model, which is not available yet. So the early design stage can improve the life cycle performance of a building. So we need early decision-making support and optimization tools, but the problem is we have multidisciplinary teams with conflicting stakeholder views. There is a lack of software interoperability and a lack of holistic data available in early design stage. And in our research project funded by the Austrian research funding agency, we aim to integrate production process planning into building design. So the overall goal is, as I said, most flexible building structure to prolong the building service life and to increase life cycle performance. And within this paper, we identified the potentials and limits for integrating processes and discipline-specific models of building and production planning and propose the framework for the BIM-based digital platform. It's the first step in our research. So the research design was we did a comprehensive literature review and a use case analysis with expert and interviews to have process mapping, model checking of all the stakeholders and data analysis. So therefore we were able to create a design process and in order to get the framework. So the design process we found out is that we have first a BIM model, but the main calculation will take place in an algorithmic model where we can integrate production process change, production processes, the data base, and multi-user VR. So here you see the framework we propose. The main platform is the algorithmic script where structural analysis and optimization takes place, and BIM model, database, and multi-user VR are coupled to it with mostly bidirectional links. So the BIM model will be the geometric and non-geometric database. We will define there the specific layer structuring, filtering, and pre-processing that the seamless data transfer is possible to the algorithmic script. We will use Archicad and Revit. And within the algorithmic script, we will use Grasshopper as visual programming language. And to the BIM model, there is Rhino Insight and Grasshopper Archicad Live Connection as connection. So within the parametric script, we have the geometry, the structural analysis, and the multi-objective optimization. The structural analysis will be with Caramba 3D, a flexible structural design on preliminary design basis. and the analysis results will be iteratively used for the multi-objective optimization of structure and layout. In the first step, we have to define the integrated database. We have to define the design space definition for multi-objective optimization. It will contain all the data for building and production design, which we need. And in ecological and technological data will be integrated. The multi-objective optimization will maximize the different objectives, maximize flexibility, minimize life cycle cost, minimize carbon emissions, and minimize recycling rate. And as I said, the values from structural analysis will be taken into account iteratively. Additionally, we will have multi-user VR, so users will be able to give their user preferences after optimization, so they can take a column, move it, or change different materials, and then a new optimization takes place. So all the different stakeholders will be able to see the building, go through the building together and see the outputs. So the conclusion is we have this BIM-based digital platform where we already tested the interfaces, and we already have our first parametric script and therefore we say we can improve the design process. And the multi-objective layout and structural design optimization will increase the building service life in long term, and the platform is a useful assistant in interdisciplinary working environments. The next steps, we will have a big use case analysis consisting of 28 real industrial construction projects in order to create the holistic database, actually, and to create a graph data model, which are the interdependencies between the different models and stakeholders. Thank you for your attention, and I'm happy to answer your questions at the Q&A. And here is also my email address if you have any further question in future. Thank you.
Thank you very much. Just to remind everyone, #3b.8 if you have questions for Julia. I would like now to invite our next presenter, Yara Saloum. So she'll be presenting from forecasting to real-time process controlling with continuous simulation model updates. Hello, Yara.
Hello.
Good morning.
Yeah,
we're just going to upload your presentation now, and the floor is yours.
Thank you. Okay. So my name is Yara Saloum, and I'm a research assistant at the University of Bochum, Germany. And I'm here now to present our paper from forecasting to a real-time processes controlling with continuous simulation model updates. So first, I will give like a small introduction about mechanized tunneling project. These projects usually contain 3 locations, so the subsurface and the surface and the shaft well are all materials transported from the delivery place to the tunnel boring machine. And the interaction between these processes is usually very sophisticated. Studies showed that the progress of the tunnel doesn't only depend on the performance of the DBM machine, but it's highly influenced by also the job site logistics. And any delay in this logistic can increase the duration of the project very, very much. So planning of such project is usually complicated. An agent-based simulation model is built in the planning phase to estimate the project duration and optimize the job site logistics. So each agent presents a process and have a state chart to organize the tasks, and the interaction between the agent is defined using messages and signals. For example, a cutting wheel agent designed by the AnyLogic software contains a state chart. It starts to advance when the ring building is finished and the required materials is available. And it goes to inoperable mode when the materials is not available or some maintenance or failures happening. The output of our simulation model gives like the number of rings installed per day, the downtime due to technical failures, and the downtime due to disturbances in the logistics, transportations also, and the delivery and the supply chain. But during the execution of the project, so some unforeseen events occur, and in addition to the level of uncertainties and the initial assumptions, the real-time progress start to deviate from the estimated one. So large deviations could increase the time and cost drastically, and countermeasures need to be taken here. So a continuous analysis during the project process is very necessary for a better control of the construction site. Online control can also be used by the same simulation model by doing some adjustment. So we can update the model and have a new estimation. The proposed concept here is to update the input of the simulation using the real-time data and rerun it. But in this simulation model cannot be resumed somehow after the update. So the trick is to restart every time a new simulation to get a new assumption. So this is not easy because we have a very large number of inputs, and some of them, as you see, is non-deterministic, and they are changing all the time during the execution of the problem. These non-deterministic data inputs are usually implemented in the simulation model using distribution functions. So we analyze the data from similar projects with the expert estimation, and we derive these functions for each input. Now, when the project starts, somehow a deviation in these inputs can happen, and if this deviation is large, now it's necessary to have a new distribution functions using the real-time data. So now, after we updated all our data, we have to implement them in the simulation model, but restarting the simulation from this new point may cause some interruption in the functions in the simulation model and interruption in the events, which can affect the validity of the simulation model. So we did a validation test here. For this test, we eliminated the uncertainty from the inputs, and we assumed a fixed input for all fixed values for all the inputs, and we run the simulation for some point. At this point, we collect all the outputs and reinsert them again in the simulation model without any change. Theoretically, we should have one-to-one results at the end because no disturbance is occurred here. In the next table here, we views the results of the validation test. We can see that a very small deviation is only detected in this validation test. And this is because we didn't update all the inputs, just the most important one. And some variables cannot be detected all the time in the simulation model. After we did the validation, we conducted a study case. We used our simulation model now as a management tool. So we will implement some disturbance in our model, a downtime in the cutting wheel for about 8 days. After we implement the disturbance, we have to update all the inputs accordingly. And because the non-deterministic nature of the model, we will run a Monte Carlo experiment for 1,000 run and collect the new prediction, the results after this. As we see, we have two results, the planning phase, and after the update, there is a deviation in the mean values and in the mode value about 7.5 days. Of course, not all the processes were affected with the cutting wheel downtime. That's why it's not one-to-one results. As we see for the future, we hope to get simulation models that interact directly with the real systems, and we have then a more reliable interaction between the real configuration and the simulation model. And thank you very much for your attention.
Thank you very much, Yara. Very good presentation. So if you have questions for Yara, hashtag 3b.9 on the chat on YouTube channel. So I would like to invite now Oh, that's a difficult one, but
Fang Zheng,
Fang's
that's right.
handling.
Morning, Ricardo.
All right. Okay, so how are you doing? So Fang will be presenting an open beam-based data mapping methodology towards structural analysis using FEM. So the floor is yours now, and we'll upload the presentation for you now. Sorry, there's a second.
Okay, so good morning, everyone. My name is Fang Zhenling from Technical University of Dresden, Germany. I would like to introduce my work titled An Open Beam-Based Data Mapping Methodology Towards Structural Analysis using Finite Element Method. So next slide, please. Thank you. We will start with the state of the art, then have a look at two ends of the proposed data mapping, namely IFC data and the data requirements of FEM. A semantic model is conceived to make a theoretical representation, and finally, conclusion and discussion are about to display. So the related research works nowadays mostly refer to data mapping from a beam model to a specific input model of a kind of simulation software. There are also many mapping projects that adopt open source FEM simulation packages, but basically the principle behind that is still the same. The input model of each kind of FEM software has its own schema to model, but eventually the input model will be converted or passed to FEM algorithm. This paper proposed a methodology for a direct data mapping from beam models to FEM algorithm. IFC models were chosen in this research work since it is much widely used and relatively developed in terms of structural analysis. The corresponding domains and objects exist already in the IFC standard. Both building objects and the connections are concerned. Beams and clones are defined as entity IFC structural members as displayed in this picture. These 1D building elements are composed by 2 points. The geometrical information hence are stored in this entity IFC Cartesian point. IFC direction indicates the object direction which is necessary in further FEM application. The data structure here demonstrates that the material parameter is stored in the entity IFC material, and the profile information is located under the entity of IFC profile depth. It refers to the cross-section parameters such as height, width, area, initial moment, and so on. Next slide. I made a mistake here. This should be the geometrical definition of 2D building elements like walls, planets, and the slabs. There are 3 different ways to define a 2D building element in IFC standard. However, all of them finally go to the loop of either vertex or Cartesian points, so that the shape and the direction are defined at the same time. Here is supposed to be the material definition of 2D elements. These references tell us how the material parameters are connected with the building objects for both curve and surface members. So connection is the other concern in this study. 1D building elements are coupled through point connections in the IFC standard. This kind of connection is defined by entity IFC structural point connection, where the coordinates and the possible boundary conditions are referenced. It is to be noticed that point connection is also applied in the connection between 1D and 2D building elements, and a curve connection is coupling definition between 2D building elements. Direction, coordinates, and boundary conditions are involved in this data structure. The IFC data architecture analysis is completed. Now we are going to check the finite element system. For static structural analysis using FEM, stiffness matrix K is the most important factor. The last equation shows how element stiffness of a beam in spectral coordinate system is defined. And finite elements are obtained by meshing a structure. After meshing, continuous modeling of finite elements are realized by coupling through nodes. Therefore, a node is supposed to contain all parameters of related finite elements. It leads to the value overlapping in the global stiffness matrix. The local coordinate system of each finite element should be transformed to fit the global coordinate system. This transformation starts with rotation around the ZX, and then rotation around the Y-axis and X-axis are also calculated. These three matrices Tz, Ty, and Tx are multiplied together as the matrix T, and the four matrices T compose the element matrix, the element transformation matrix. The order of rotation is not fixed. It can be changed, depends on the real situation. So the stiffness matrix of 2D finite element is way complicated than being elements with respect to the shape functions, the model approximation on the different strain stress scenarios. Hence, it's not deep studied yet. Based on the preceding work, the topological and the logic relations of the required data of structural analysis using FEM are represented in this UML diagram. A meshed structure has nodes and finite elements can be formulated by an equilibrium equation. A node coordinates material parameters and constraints. Coordinates can be acquired by geometric parameters. Coefficient of cross-section are part of them as well, and the mechanical parameters can be calculated through them. The mapping possibility from IFC model is also investigated. We proposed a data mapping methodology, studied both IFC data and the architecture and the data requirements of structural analysis using FEM. Based on the analysis result, a semantic model was established. In the future, the case study should be completed through programming and in an automatic way, and the 2D building elements should be a more complicated issue that need to be intensively studied and solved. Accordingly, the semantic model also should be further enriched. So that's it. Thanks.
Thank you very much, Fang. So just to remind everyone on the chat group that if you have questions, so you need to start with hashtag 3b.10, and then we will discuss later in our Q&A session. I would like to invite now Kjeld or Kjeld. Kjeld, and he will be presenting real-time evaluation of room acoustics using IFC-based virtual reality and oralization in engines. So the floor is yours now.
Yep, thank you. Yes, as you can see, I'm one of many authors of this paper and many participants in the project behind it. And yeah, we can take next slide. So the project this research comes from, was done from January 2017 to October 2019. It originated from an idea from the engineering company Corvi, who wanted to look into possibilities of using virtual reality and augmented reality in the engineering company. And we ended up with three main partners, the engineering company and the technology development company, Epito, and Aalborg University, where we involved three different departments. So the main goals of the project were to identify possibilities and challenges in the use of virtual reality and augmented reality in this engineering company, and we should try to develop some prototype to demonstrate some of the new possibilities. So we had an initial dialogue with several departments in the engineering company, and yeah, ended up with deciding on two main tracks, one with augmented reality in infrastructure, which I will not talk about today, and the other one was virtual reality and acoustics in the indoor environment. So I think most of us have experienced indoor environments with very poor acoustic quality, and the engineers are actually able to make good indoor environment quality regarding acoustic also. We have very good engineers who can design the acoustics. So we ended up to try to design a system that we could be using in the very early stages of design, and the engineers designing, for example, ventilation systems could in combination with virtual reality visualization, also give the client an impression of the acoustic environment. And that's quite complex. So we developed a system where we could use the BIM models. We could add some audio recordings from relevant sound sources. We can put them together in a setup where we could demonstrate it. I'll go through a few challenges we had in this. For example, setting up the acoustic room. We used a very simplified aerosolization engine with very simple geometry, which gave some challenges in setting up the acoustic room. Only shoebox-shaped rooms and only one kind of properties, acoustic properties on each face of the room, and so on. And we could only handle point sources, so we could not, for example, have an entire wall as a sound source representing sound from a neighboring room. So we, for example, looking at handling the sound source from an entire surface, then we show here how we try to make different locations of several point sources to represent a phase source, so it would be experienced as a phase source in reality. Another challenge is sound level. We have sound recordings which should be recorded and brought through the system, and in the end played in our headphones at the correct sound level. So those had to be calibrated all the way through this process. So we developed this system to handle that. According to reverberation time, the acoustic engine simulates or adds reverberation to the sounds we have put into the system. This means we must not have reverberation included in the recording. So we needed recordings from an anechoic room. So we have brought different types of equipment that would be relevant for our simulations into our anechoic room, and made these recordings with calibrated microphones, and where we could bring the data all through the system until the specific headphones used in the virtual reality system, so we could play the sounds with the correct level and with only reverberation added from the acoustic simulation in the system. So those are a few challenges. We have tested the system with users from the engineering company, different kinds of virtual reality setups. And this is an example from one of these tests where we simulate. And this slide is not easy to see, but just to show the complexity of, say, the future workflow that could be used in the company if this kind of simulation should be used in the design processes, in the dialogue with the clients. So conclusions. We think a system like this could actually lead to better acoustic designs of, say, ordinary buildings where you would not normally introduce very advanced acoustic simulations. But we can also see that there are still many challenges to overcome, and it's at the current stage, we see it as a prototype that would not be that easy for the normal design engineer to use in his daily work. So it needs to be streamlined a little bit more, because there are many challenges to handle the correct sound sources and combine them with the BIM models in the setup, and bring this forward to the dialogue with the customer in the end. Yes, thank you.
Thank you very much for your presentation. Just to remind everyone, if you have questions, #3b.11 on the chat room. And I would like to invite our last presenter of this session today, which is Ellie Daher, and the article, A Participative Framework Covering Urban Planning Process with Parametric Approach. Thank you very much. We're going to upload your presentation now.
So, good morning. I will be presenting this paper co-authored with Sylvain Kubisky. So I'm also now finishing my PhD thesis. And this paper is about participatory framework covering urban planning process with a parametric approach. So next slide. So the change in urban meanings is taking place in different levels due to the increased number of urban spaces, which is also creating some challenges for environment and human health. So the urban planning process is developed according to different stage, and there is a belief that we should include the participation and engage the citizen in the urban planning, which has already started since the 60s, where we see different wave of participation and the design process of urban planning, engaging the end users and citizen in the design process. And on the other hand, the adoption of new technologies and method in architecture and construction, especially in parametric design, have also shifted the practice of professional and education, where we see different practices covering also the urban planning. However, we can see that these practices are not covering the participation. So here, maybe you should please shift. You should, yeah, next, because there's an animation here. So there's a multiple problem actually covering the urban planning, which is based on manual sketching. There's no informed data, and evaluation of the design is coming into later stage, where if we want to make some modification, so it will cost more money or due to the design loop, and the participation process is limited and is only limited to the verbal participation. So the research question, how to enable participation in urban design with the use of parametric modeling design approach. So the objectives of this paper or this work is to shift for a collective thinking, where we engage also citizen and inhabitants to contribute in the development of cities and our smart cities. And also to fill the gap between the participation from one hand and the urban process in the other hand. So we created a design process we developed based on different steps and interaction that I'm going to show with these interaction later. So these design steps cover main design steps or stage of the early design process of urban planning. And to support this design process, we are using also some digital tools that enhance or improve the participation of the citizen in the process, like a tangible table, mobiles, and augmented and virtual reality. So now I'm going to show some of these steps of the design. So the first step and second step, where we invite the citizen to input their criteria. So we are engaging the citizen in the early design stage of designing the process of the urban planning. And then we invite them to understand the diagnostic of the site based on criteria that have been that have been set by them, like noise, view to sky, pollution, view, and other criteria can also be implemented. In the next step of the design process, so we invite them to explore the design or the site and to see the suitable functions on the site by having a recommendation system based on fuzzy logic to analyze the fitting suitability between the urban requirements and the site. In the next step, we invite them to allocate and make the organigram, the first organigram of the design of the urban space, and to explore different recommendations about the function allocated using tangible table and physical object. And then we start by another interaction, which is related to the urban pattern or urban structure, where they can use between different structure, or they can get to a manual sketching, a rectangular urban pattern or other pattern that can also be implemented. in the next stage, actually, we start generating the 3D urban typology based on the different parameters that the end users and expert have identified, and we have different strategies of urban typology. And in the last step, we invite them also to explore the simulation of these solution by different indicators and features. And to experiment this prototype, we conducted 3 types of experimentation. First of all, we started by interviewing experts in Luxembourg, and then we conducted one virtual workshop and another individual workshop due to the COVID situation where we couldn't have many people together. So as a findings, the perception of expert by the interview, so they strongly agree that there's a potential to use this type of prototype, and they mostly are based, their work is mostly based on workshop prototype with citizen. And also they agreed that there's no human interaction when using digital tools. As the perception of the expert when we conducted the webinar, most of the experts find that this interaction can enhance the transparency between the expert and the end users, and also the end users or the citizen, they agreed that this type of interaction or prototype also provide a transparency process between the expert and the citizen from the other side. So as a conclusion, we conclude that this prototype can provide an evaluation of the design criteria with an instant process way, enabling the end users to understand more the design solution and to involve them in the design of their own for future. And thank you for listening. And if you have any questions, please.
Yeah, no, thank you very much. So in the chat room, if you have questions for Eli, please #3b.12. So I would like to invite all presenters for this session now. So I can see there has been a few questions for 3b7, which is Thais. Thais, we're going to just revisit, so if people are not following or reading the chat room, right? So if you could read your answers. So Sylvia asked, you say that the CASB and DGNB are the only DRS considering scientific LCA according to what study. Which kind of stakeholders are able to do it, professionals versus researchers?
Well, thanks. That's a really good question. So DGNB and CASB are the only ones that actually it's mandatory to do an LCA. So the assessment goes, it's not a process apart from the certification process. So ideally, designers in general, and when I say designers, it's architects, engineers, they should be able to do the assessment by themselves. But as I was going through all the requirements, they are very complicated, like they look very apart from the design process itself. So yeah. I hope I answered the question.
Yeah, no, it's okay. Thank you very much. Now I have a question to, a skilled Slits, yeah. So Robert Arm was saying, wow, this looks exceptionally complex. Even getting recording of all potential sound sources to run into VR would be a huge task, let alone combining many sources into the VR environment. I think it's about the experience of doing that. So can you comment about the complexity of the task?
Yeah, I think that is actually...
Sorry, apologies to interrupt you. There's a question from Jacob, which is, are we anywhere near reusable acoustic simulation building blocks for everyday design? So. combined question.
Yeah, okay, yeah. So we take Jacob's question. I'm not quite sure what you mean by reusable, but I think we demonstrated with this that it is actually possible to do some quite realistic simulation with these very simplified real-time acoustic engines. So we tested, I mentioned here, this AMD 3D. So this is an engine you can include in your own software, so where they have made some tricks to make, you say, there's a lot of, it's not very accurate, but it sounds correct at the end. And similarly, Google has something called Resonance, a similar engine that you can integrate into your virtual reality solutions. So there are tools that can do this quite accurately. I think the big challenge is what Robert mentions, that to do this in a proper way, we need to have recordings of relevant sound sources in a very high quality. We don't have libraries of that, so we don't have a library of sound sources recorded in anechoic environments where you know the exact levels with which microphones they are recorded. So I mean, we basically don't have the material. But what we consider is, how many, for example, how many different ventilators do you need to record to have a sufficient representation of a ventilator? How many different recordings do you need of projectors sitting in the ceiling? So sounds. So how many typical sound sources can we reduce it to have a sufficient library? But I mean, this is still a big challenge. What was this second?
Right, thank you very much. So there's another question for Ellie now. Minor question: how are the tangibles chosen to represent different functions, areas, aspects on the table?
Just come back.
Is Ellie gone? I think he's gone. We might need to bring him back later. So meanwhile, just a quick one for you again, Kjeld. So thank you for your presentation. Which component properties need to be included to run the auralization analysis?
Yeah, you probably mean building components. So we need we need acoustic properties of all surfaces in the room, and we of course need, you could say, acoustic properties and recordings of sound sources in the room. So that would be, yeah, any machinery in the room, or any sound sources from ventilation systems, sounds from adjacent rooms, which should be represented somehow to put in as a source in our simulation.
Okay, thank you very much. So Ellie is back, and now Ellie, the question for you is how were the tangibles chosen to represent different functions, areas, and aspects on the table?
Okay. So actually, what we try to do is to simplify these illustration of functions with the tangible object viewed on the tangible table. By choosing very simplified 3D illustration of each function to represent presented. So and then we were also figuring out if there is another possibilities to illustrate these functions by other type of tangibles. So we tried. So we have another also illustration with 2D drawings actually, but then we found that 3D objects are better to illustrate the function.
Okay, thank you very much. So we have a question from Fang. So Fang, if you allow me to call you Fang. Schuling is asking you, thank you for your presentation. Could you explain more about how the meshing effect work from IFC to the modeled objects?
So actually, this is a very essential part that does not elaborated in my research work in this paper, because in IFC standard only objects are defined, but they have to be somehow transformed into several elements. And I can't explain more about something more about that, but I will when I try to automate this process through programming, I will take this part into consideration and solve this somehow. But now there's no answer for that. Sorry.
No, it's okay. At least it drives the research. So I have a question for Julia. Julia, I do quite a lot of work in healthcare environment where flexibility, structural flexibility, is particularly important, right? So from the work you've been doing so far, what are the aspects of flexibility that you see are more important or more relevant for, particularly for stakeholders?
So you mean flexibility not just on building structure side, but flexibility in the whole design process?
No, but building a structure as well, because you can make flexible in various ways, I would say.
So we already conducted some expert interviews, and so the most important parts for maximum flexibility is, of course, the production hall height. So you should have reserve in the height that you can implement something afterwards. Then you should have the maximum free span width. So with the best in the best solution, you have no columns within the hall, but of course this is also conflicting with costs and possibility and material demand. So these are conflicting goals, and the most important part is the selection of the construction type. If you have a truss or if you have solid girders, so trusses are more wished for in production planning, because we are also including building service equipment aspects in our research, so you can go with all the pipes and heating systems through the truss. So this would be also a better option.
Yeah, there's just a quick comment. I just had a PhD who finished her work on DFMA, and I think there's a strong relation to the work that you're doing. So just a comment now. And a question for Yara. Yara, how do you get updated information? And how often do you need to get updated information to upload it to your system?
So the update mainly, as we said, like we have two types of data. Some data from the project, they don't change, like the specification of the machine, for an example. Some data we have to update directly, like the length of the tunnel, how many rings we have already installed, how many grout and materials we have in stock, we have in the tanks. Such data we can collect directly from the construction site, and we can implement directly also in the simulation model. So now we don't start from the 0 point, but we start like from the actual status of the project. But the non-deterministic inputs we talk about, like how the duration of building one ring, and the duration maybe for the technical failures. These numbers, we cannot just directly take it from the project because it's changing all the time. And we already made some assumption from the beginning for these durations, using data, as we said, from old projects, and some assumptions from the experts who's planning the project. Sometimes when we see like there is a deviation in these assumptions, we have to analyze the data again. So we don't use only all data from other projects, but we use only the data collected from our project. So we see like the failures are more than we expected, or they are less, or the durations are more or less, and we have to analyze this data again. Then we have new functions. And these new functions we have to implement in the simulation model for the next phase of the simulation. This is what we talk about updating.
Okay, well, thank you very much. I'm gonna, be made a little bit of a dictator since I have this post as a chair. I'm gonna use the time that we have. Killed. One of the things that we found here in our studies, right, is that regulations and codes for schools in relation to acoustics, they focus on kids, not so much in teachers, and 1/3 of the causes of absence for teachers is voice problems because poor acoustics in schools. So the extent that you can test the Lombard effect in your environment, is it possible? Have you done any tests on that?
Yes, I think we see this kind of tool as an initial analysis in the early design stage, where you could possibly identify the need to make more advanced simulations, because I think, this is still very simplified analysis we are introducing, but what we found in the engineering company is that clients are often reluctant to pay for acoustic analysis. So, and acoustic analysis is normally very expensive because it's very specialized people and it takes time to set up the models and so on. So the idea with this was that in the early stage, you could actually give a quite realistic idea of where we're heading regarding different design decisions, and then you could decide to make more advanced analysis. So I think this could, so I would say, yes, this could help in identifying possible problems in an early stage, and then you could put more effort into the acoustic design.
Okay, well, it's good to see that it's progressing in that way. So I might be in touch in the future. So I'm just going to the chat room now, and I cannot see further questions. Well, I would like to thank you all for your presentations. Also, I would like to wish you well, considering all the circumstances that we are experiencing worldwide in terms of pandemics. And it was really interesting to see that as a whole session, we are working towards better data validation, better data quality as well, which has been a struggle. And also that we've been focusing on developing further our standards, even though my perception is that industry in general, not very keen on adopting standards. They keep developing their own standards, but that is a comment as an academic. Yeah, well, keep up with the very good work, and thank you all for your participation, and I hope I haven't done too badly as a chair of this session. Thank you all, and have a nice day.
Thank you very much.
Thank you.
Thank you.
Bye.
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 Thank you.